Hello and welcome to another video. Today we're going to be working on word search. So in this problem you're given an m by n grid of characters, board, and a string word, and you want to return true if the word exists. Now the word has to exist by going down some characters and you can't go backwards. So for example, you can't go like ABC and then back here, right? You can't repeat previous characters you've used. So in the first example, we are looking for A, B, C, C, E, D, and as you can see, it is there. In the second example, you're looking for C, and it is right there. And then the third example, you're looking for A, B, C, B. And if you look like anywhere from A, so if you try to go here, there is no, you can't go back, right? So there's no A, B, C, B there. And then there's another A here, but there's no B, so you can't find the word. So, and also the constraints of this problem are something like n and m are like 10 or something around there, and then the word length is like 15 characters, so really small. So when you see these constraints, it's a big hint that you're going to use some kind of inefficient algorithm typically, right? Because it's not going to be a super efficient problem essentially. So let's figure out how we can do this, and let's just think about it logically. Like logically, let's say we're looking for this word, right? A, B, C, C, E, D. Like what would we do? Well, logically, if you think about it, you would just like look for an A, and then you'd from that A see like is there a B, and so on, right? You would try to look at the starting points, and you'd see like where can I go? And that's kind of what we're going to be essentially doing. Is we're going to loop through this matrix, and we're just going to say like, hey, we're looking for A, B, C. CED, so let's just loop through this matrix and look for an A, and then anytime we find an A, we can call some algorithm that will find the rest of it. Because if we look through the matrix and we, or I mean, actually, I guess our algorithm can technically handle that, right? So we can technically just pass everything into our algorithm, and then our algorithm can handle it. But, so what does our algorithm kind of need to be doing? Well, essentially, it needs to be like let's say we pass in this value. Our algorithm needs to maintain like the row and the column we're on, and also what letter we're comparing to, right? So when we first start looking for the word, we're looking for an A, right? Like logically, you would look for an A. So you'd like go into here, and you'd say, okay, we found an A. Now we're gonna look in like every other direction, and we're gonna look for the B, and we're gonna say, okay, well we found a B over here. And now from the B, we're gonna look everywhere for the C, and we're gonna say, okay, we found it over here. And then we look for this next C, and so on, right? Until you find the exact word. And then once you find the whole word, then you would return true. But if you go to somewhere and your character doesn't match, for example, you are here, let's say, and you are looking, so let's say we are at the C and we're looking for an E and we go to the S instead. We'll say like, oh, that doesn't match. So let's go back and try something else. So it's essentially backtracking where you are at some place and you need to look in every direction for some character. And if it doesn't work, then you need to go back, right? Like, let's say we were looking for our A, B, C, C, E, D, and, let's say this was like, let's actually copy this, maybe. Let's actually draw it down here, just to make it a little more straightforward. So, do this. More like a parallelogram than a rectangle, but it is what it is. E, S, E, C. And let's say we look for, so there is this ED, but also there is like an ER or something, right? And then this is whatever. So let's say we are going down this thing and we are, okay, A, B, C, C, great. But now we are looking for ED and we just have to go this way. Actually, I guess here you would find it, right? So maybe this is not the best. Oh yeah, let's actually get rid of a little bit of stuff here just to make it. So let's say it's not here. Let's say this is whatever, RR. All right, let's change the letter as well. RR. But, for example, we change this letter to an E. Now let's kind of see what happens. So we change this to an E. And then we say, okay, well, so we have A, B, C, C, but then we decide to go right instead of down. And now we can't really go here, right? So we needed a D, we can't really go there. So we need to actually go this way, but we can't really go there either because this needs to be a D. So essentially you're just backtracking, right? You are going down, and anytime you hit a letter that you didn't expect, you just go back to the previous letter and you keep doing that. So what's our backtracking algorithm going to look like, right? Well, what's our base case for the backtracking algorithm? The base case is, let's write it down. Base case, if we found every letter, right? Every letter and the index we are looking for now is length of the word. So for example, or you could do it another way, right? You could also check like if the index you are looking for is length of the word -1, that would also work, I guess, technically. So let's say we have a matching letter and then the index is the length of the word -1. That would also work, right? So length of the word -1. So for example, here for this A, B, C, C, E, D, so if we draw that out, A, B, C, C, E, D, this is index 0, 1, 2, 3, 4, 5. So we can just say, like, if the index is 5 and the D matches, then we're done, and we just return true. Right? So we can return true. We also forgot what are our actual arguments going to be. Well, it's going to be a row, it's going to be a column, and we also need to know, like, the current index we're on, right? What letter we're looking for. And also note, this problem is not like a typical DP problem because let's say you are on this index and you are here. In a typical DP problem, it doesn't really matter where you came from, right? You could just say like, oh, look, yeah, sure, I can find it. But in this problem, it does, because you're going to come from somewhere, and all that stuff you came from, like let's say you came from here, it does matter. Like this is a different state than, let's say, this, because you can't go to letters you've already been to. So it's not identical. So like coming here from other letters makes a difference. And when that's the case, you can't just do normal DP because you might go to letters that you've been to already, right? So that's the way you want to think about DPs, is like when I get to a state, does it matter how I got here, or are they all equivalent? And in this case, it does matter, right? Like this, like I said, is different than this because let's say you are here, you can't go back over here, but if you came this way, then you can't go back over here, but you can go this way, right? So that's why it's different. But yeah, we're going to have a row, column, and index, and like, what's our recursive case, essentially? So recursive case, we're going to check, are we out of bounds, right? And we are going to check every single direction, but like, what if we were over here and we just went up and we're out of bounds? Well, that doesn't work, right? So if we're out of bounds or the letter we are looking for doesn't match. For example, let's say we're looking for this ABCC and then we come to this E. Well, then that's not the letter we want, so we'd have to go back, right? And then there is one more thing, right? How do we ensure we don't have infinite loops? So like, you know, we come over here and come over here. Like, how do we make sure we don't go backwards? So there's a few ways you could do it. One way is as you go, you can have a visited set. And then like as you recurse, you would just delete things from the visited set. So what that would look like is like, let's say you go to this A, you would add this row, column to visited set, go here, add them both to visited set, go here, add them both to visited set. Let's say you go to the wrong place, like you come here, add these to visited set, and then you look for the, what's the last letter? The D, and you look like over here, and you're like, oh, that's wrong. Okay, well, can I go here? No. Can I go here? No. Okay, I've ran out of places to go, so now I need to actually delete this. Well, it was just that one line, and then I need to get rid of this out of the visited set. So as you backtrack, you would get things out of the visited set. So you would say like add the visited, backtrack, remove from visited. That's one way you could do it. Now what we are going to do is, it says that every character is from A to Z. So we're just going to make the character that we visit something, like we're just going to make it an exclamation mark. So what that's going to look like is we're going to go to A. We're going to say, okay, we visited that. Let's make that an exclamation mark. Let's go to B. We visited that. Let's make that an exclamation mark. And then when we visit other locations, we're just going to say, anytime we get to an exclamation mark, let's just return false because we've already been there. So we're going to go to C, exclamation mark, and so on. And then if you need to backtrack, like let's say you come over here and you can't go anywhere, then you would just turn this exclamation mark back into an E. And that's going to be easy to do because we are going to pass in the index we are looking for. So if the E matches, we know what to turn it back to because we have the index in the word where it matches, and we can just turn it back afterwards. So now our thing is going to be check for match, letter match, If no, return false right away. If yes, change letter to this, and then backtrack, and then change back. Or you could do a visited set. Like if people, if you had an interview and it was like you can't manipulate your input, then you can just use a visited set, which would be exactly the same thing. But now we have kind of everything we need. So essentially we're going to be looping through every single letter, and we are going to have this backtrack function that will just take a row column index. Even though it takes a lot of variables, like I said, these are all like 10 or so. It's very small, so it's fine. And yeah, pretty much we're just going to be checking, and then whenever we found the whole word, we're going to return true. Otherwise, we're going to return false. And then we have to loop through every single starting index. And if there's any one starting index that returns true, that means we found the word. And that's pretty much going to be it. And yes, for every single index, we're going to go left, right, up, down. And yeah, we're going to see if we can find the whole thing. So now I think we have enough to code it up. So we're going to make a directions array as I normally do my Python videos. So I'm going to say directions array is going to be, and we don't need to give it a type because it's already initialized to an array, nested array of numbers. So like that's all it can be. And we're going to make -1 0 and 0 -1. Probably space it out a bit as well. There we go. Okay. So let's do this. And let's also make rows and columns, as I also do in the Python videos, because we are going to use those that are just going to be constant numbers representing the width and the length of the board. Okay, now we're going to make a backtrack function. So it's going to take a row, which is a number, a column, which is a number, and an index, which is a number, and it will return a Boolean, true or false, if we found the word or not. And then we're going to write it. And so we are going to check if the thing is invalid, right? So let's do that first. So if row is less than 0, if we're like out of bounds or like all these other cases, or if row is greater than or equal to rows, or column, actually give us more space here, or column is less than 0, or column is greater than or equal to columns, or the letter doesn't match, right? So board row column does not equal, and that's why we are going to change these things to exclamation marks to make sure they don't. So if any one of these is true, if we're either out of bounds or the letter doesn't match, we can just return false. And now, if the letter does match, and we are on the last index, so if index equals, it's going to be word.length -1, that means we've matched every letter, so we can return true. Okay, now we are going to change the character to an exclamation mark, so that way we don't revisit it later, because if we did, then this would be false, so we wouldn't do it. We wouldn't like go through it again, essentially. Okay. Now we have to actually loop through all of our directions, so we can just say, and you can actually destructure, so you can say like row add or something, whatever you want to call it, or like new row, or whatever. I'm just going to call it new row. It's technically not new row. But essentially, this is what you need to be adding to the row and the column to get it. So we can destructure. So what that would do is, like, for example, the first element would be 1, 0, new row would be 1, new column would be 0. Okay, so we could say if backtrack row plus new row, right? New row is just really what you add to the row. And column plus new column. And the next index we need to look for, then we can return true here. Okay. Yeah. So we loop through that, and now what do we need to do afterwards? So remember, we did our backtracking. Now we actually need to change our character back because we've used, like, we're not going to traverse from this character anymore, but we need to change it back because we might need to use it later. So we're going to say board row column equals, and then what was it before? Well, it was just word index, right? Because they have to be matching for this to happen. So that was the word, that was the character that it was before. And then finally, when we went through everything, we can just return false, saying like, hey, we tried everything from here. We didn't find anything. Let's just return false. So now we have to have a loop that loops through every single possible starting character for this. So we have to say for let row equals 0, row is less than rows, row equals plus, for let column equals 0, call is less than calls. So if backtrack from whatever row and column, and what's the index? Well, the index is just going to be the starting character of the word, right? Like we have to match the entire word. If this is true, if we could match it from this location, let's return true, and we don't need to look for anything else. And finally, if we went through our whole matrix and found absolutely nothing, then we can just, as a default, return false. And hopefully that works. Let's see. Looks like it does. So let's do the time and space complexity for this. And it's going to be kind of tricky because it's a backtracking, but let's give it our best shot. So let's go through here. So this directions and rows obviously all have 1. Now this backtrack function has something, and then you also have this loop. So this loop is m by n, obviously, because you are checking every single starting index. And then now you want to figure out like how expensive this backtracking is. So backtracking is usually however many choices you have to the power of like how many times you have that choice. So you can argue like two things here. You can argue like we are technically checking 4 directions, but realistically, if we go to a direction that we've explored again, we will just basically return false right away. So you could argue it would be like either 3 or 4. I'm going to say 3 because like I said, if this doesn't really matter. Like if you write this before backtracking, it doesn't really matter essentially. Like you could check here just to make sure that like these are valid locations if you wanted to. But yeah, I don't think it really matters in terms of time and space. So I would say because we only have 3 choices, we can't go back. And it could be less than that. Like it's worst case 3 choices. Because as you can see, like even if you go forward, but it could be a lot less choices because let's say you go to D and then you go to F and then you go to S. Well, now from S you can really only go to 1 and so on, right? So minimum it's going to be well, I guess at the first letter you have 4 choices, but at every other letter you have 3. So but yeah, either way, either 3 or 4, and then I'm gonna write 3, but maybe you can argue 4. I guess actually I probably should write 4 because at the first letter you technically do have 4 and it's the worst case, so we'll just leave it at that. Okay, and so now we have to figure out like how many times we get to make that choice. So if you think about it, the number of times you get to make that choice is the length of the word here, right? At every single location you have 4 choices. So how many how many choices do you like how many times do you get to make a choice? What's the length of the word, right? You're traversing every single letter. You can't traverse more than the length of the word. So it would be 4 to the length of the word, which is we'll call that W. And then the space. And yeah, the nice thing is the reason this works is because this word is not too big. So okay. Actually, yeah, I don't know. 3 or 4, like I said, arguable, hard to say. These backtracking functions are always like a huge pain for time and space. But actually, the space is easier for this one because this is constant space because there's only 4 elements. Constant space. Now, we are modifying in place, but even if we weren't, it would be easy to figure out what the space is. And yeah, so the space here, actually, we do have to account one thing. Like, even though this is technically of 1, you do have to account the recursive call, right? The recursive call stack. So what's the farthest down the recursive call stack can be if you think about it? Like, how many stack frames do we need, essentially? Well, if you think about it, the farthest down we can ever recurse is the length of the word, right? We can't go more than the length of the word because we'd just be out of bounds. So that's going to be W here, is our space. And yeah, it's going to be it for this video. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one probably tomorrow. So thanks for watching.